Welcome to Didactic. Today is Friday, May 3rd, 2024. I am Dr. O'Leary, a nearly full-grown psychiatry resident in the National Capital Region. What this means is that next month, I will graduate from residency, and aside from getting a big raise, I will also be able to be called attending or staff psychiatrist. I started this podcast about halfway through my second year, and this is the 58th episode. I started this podcast, thinking that it would be a structured resource for residents for learning various topics, but it became much more than that. Every time I do a deep dive into a particular topic, I get inspired. There's so much we don't know about psychiatry and neuroscience, but there's also so much that we're learning. It can be hard to find all the information about a topic and make sense of it. But if you're willing to let me try, I will do that for you. I will try to do that for you. I will read a bunch of papers, listen to hours of talks, and then try to say something meaningful about it. I do not always succeed at being smart, but despite the fact that I often cringe at what I've said in the past, I keep doing it because for me, it has been one of the most rewarding learning experiences of my life. Forcing myself to do this podcast makes me feel a constant sense of renewal and accomplishment. No one has told me to do it, and I am the only one responsible for its content. For new listeners, thank you for arriving. For repeat listeners, thank you for coming back. Today, I'm going to discuss what just might be the most under-discussed part of the brain, the cerebellum. As a medical student, I was taught that the primary function of the cerebellum is to fine-tune our motor movements by responding to the sense of our body parts in space, which we call proprioception, and the amount of force that we're putting on something, in what direction that we're moving. The classical clinical test for doctors is to have a patient touch their nose, then have them try to touch the doctor's finger that's held about 2 feet in front of the patient. A classic positive sign that there is a cerebellar problem is that the finger has a hard time trying to stay on track. It's not due to some kind of tremor, but due to the brain's inability to adjust the arm's position with precision. Especially as your arm gets further from your body, the finger deviates even more from the target and kind of has to be reined back in a jerky kind of fashion. I did not until recently even consider the cerebellum when thinking about psychiatric conditions, but the more I read, the more I wonder why the cerebellum is not considered a potentially important player in nearly every psychiatric disorder there is. Although it can be said that all brain regions primarily function to make predictions, the cerebellum is especially active at refining impromptu predictions through short periods of time as sensory data is changing, and it helps us better navigate the world, not only in physical space, but social space and our internal space. The cerebellum gets ignored quite often because it's hiding in the back of the skull, tucked away under a sheet of dura mater, and seemingly inconsequential for most of what we think we do. When it doesn't work, when the cerebellum doesn't work, we can still move. We're just clumsy. If I were to tell you that our cerebral cortex has about 16 billion neurons, how many neurons would you estimate the relatively diminutive cerebellum has? Maybe 4 or 2 billion? The answer is about 69 billion neurons. Have you ever heard that we use only about 10% of our brains? This false fact in part comes from the fact that when we first started measuring the brain, we could only really measure what the brain could sense, what we could see the brain sensing, and what actions it could make our muscles do. The prefrontal cortex, for example, was thought to be kind of an extraneous silent mass. But now we know that it does so much. We now know that without the prefrontal cortex, we wouldn't be able to even learn about the prefrontal cortex. And the same is true for the cerebellum. The cerebellum is connected to every other brain region extensively. It has more dedicated computing power in its pinky than the cortex can muster in every one of its regions on overdrive. The cerebellum needs this computing power because it appears that it is constantly building impromptu models, not only of like the recent present, but simultaneously of the near future. I mean, how else could it keep that finger on track without wandering off in some random direction? Based on the current trajectory, it needs to be able to predict in milliseconds how to adjust our motor output and not just calculate that, but communicate that to our premotor and motor cortex and our striatum. It can do these calculations for far more than fingers, and it can do it while simultaneously rebuilding its own model every time an error is detected. The cerebellum optimizes our movements, and it also optimizes our self-referential thoughts, our immediate and future plans, our social awareness, and in short, it increases the precision of the predictions that every other part of our brain is making. Even cooler is the fact that the neurons throughout the cerebellum are arranged in basically a universally preserved motif, which means that the function that they perform is basically the same, whether you are moving or you're responding to a joke. The same kind of function is useful for everything we think and do, kind of similar to how a transformer like those used in AI, like ChatGPT, the transformer, can use the same basic architecture to output probabilities about just anything, and it can help select the next best response. I am so impressed with the cerebellum right now. It is my new favorite neuronal mass. Now, for those who have listened to the podcast before, you know I nerd out over things like Bayesian reasoning, and I have characterized the brain as more or less a giant Bayesian calculator, but it wasn't until I started reading about the cerebellum that I finally started to understand how powerful this Bayesian calculator can actually be. For those who need a really quick primer, Bayesian reasoning is a way of basically using conditional probabilities to predict the future. Now let me put that into some kind of necessarily mathy English. The cerebellum and the rest of your brain can calculate the probability of some outcome given the current state of the world. Now, calculating the outcome relies on knowing or assuming that the current state of the world that it is inferring is true, and then it needs to know where it wants to be and has to predict how to get there. So before I inspire you to turn off this podcast, let me talk a little bit about how this matters. Let's say someone says this sentence: "You're such an asshole." And then they laugh. This could mean many different things. I mean, they could be ridiculing you or criticizing you or accusing you. They might also be ribbing you or cajoling you or sharing some kind of inside joke. Almost certainly, when something like this is said by someone and they have never said it before, your brain throws an error signal. Suddenly, a lot of processing power is recruited to figure out what this means. It gives you pause. During that pause, your cerebellum is going wild, trying to help you calculate the most probable meaning of the statement and a good response. In the 1990s, the first well-supported hypotheses about the cerebellum's role in psychology began to appear. For example, a 1998 paper by Andreessen, Paradiso, and O'Leary, no close relation of mine that I'm aware of, discussed an idea called cognitive dysmetria. Now, see this show's transcripts at psychiatric.buzzsprout.com for references here and throughout the rest of the podcast. Now, think about that example of the asshole statement that I just gave. There are many directions that you could respond to that. A person could also not respond at all. I mean, they might laugh, they might act indignant, they might verbally attack the person saying it. All of these directions are decided in your brain based on the probability that any of them is the best action given the current sensory information. Your affective state, other sensory information that's coming in, maybe like the intensity of the sun, your working memory for recent events, your present goals, the intention that you have for being in the place that you are, and your available memories, among many other things, are all contributing to a calculation of the best response. And your cerebellum is doing a lot of this math. When the cerebellum is doing math related to your movements, it has direct sensory fibers to the body feeding it information, and it also is getting information from things like the motor cortex and the premotor cortex. When it's doing math about social situations, it's also getting a load of information about what is happening in the cortex, and it's trying to figure out what is the most important information. Now, it's easier and more obvious for us to see the cerebellum's effects on positioning our body in space than it is to see its effects on positioning yourself in a social context. I mean, it's also easier to position your body in space than in a social context. I mean, the cerebellum is comparing direct signals about your body's position in space when you're moving and trying to stay still, like when you're standing in one place, but you're still moving a little bit in order to keep yourself in that place. And it's processing errors between the predicted and the actual placement of the body. In this way, it sends signals kind of to the thalamus and the cortex, and it's making immediately needed adjustments. How does it adjust our position in social space, or in temporal space, or in affective space? Now, this brings me to something called cerebellar cognitive affective syndrome, and it's sometimes referred to as Schmahmann syndrome after Dr. Jeremy Schmahmann, if I'm saying that right. He's a professor of neurology at Harvard Medical School, and he first described this syndrome in detail. Now, let me give you an abbreviated quote from a paper called The Cerebellar Cognitive Affective Schmahmann Syndrome, a task force paper, and it's from the journal Cerebellum, published in 2020. Here, I summarize what parts of the cerebellum have been consistently associated with different cognitive and affective states. Deficits in linguistic, visuospatial, and executive function were held to result from the disrupted connectivity between the posterior lobe of the cerebellum and, quote, cerebral association areas, especially prefrontal cortical areas, in relation to executive control, parietal cortical areas with respect to visuospatial function, and frontotemporal regions in relation to linguistic function. Affective emotional disturbance was seen as associated with lesions in the limbic cerebellum, associated with the vermis and the vestigial connections with the reticular nuclei in the brainstem, intralaminar and anterior thalamic nuclei, the hypothalamus, as well as the hippocampus, septum, amygdala, ventral tegmental area, periaqueductal gray and mammillary bodies, cingulate gyrus, and pregenual, retrosplenial, and paralimbic neocortical regions, unquote. Now, I encourage you to go to YouTube and search for Schmahmann syndrome or cerebellar cognitive affective syndrome because I cannot do it justice here. Schmahmann reports that children born without a cerebellum actually have relatively minor motor problems, at least compared to the substantial deficits in intellectual functioning and in language, in visuospatial processing, and in executive functioning. The posterior lobe of the cerebellum, in particular, appears to be integral in language, cognition, spatial learning, executive function, and affective learning. The problems with language in persons with cerebellar injuries, like strokes or other lesions, or developmental problems, are not aphasias. It's not that they can't speak. They can speak, but they particularly have difficulty with things like ambiguity, sarcasm, implied meanings given the context, metaphors, and inferences. Additionally, the cerebellum appears to be necessary for our theory of mind. Now, Dr. Schmahmann also describes multiple patients with Chiari malformations. Now, these are malformations of the skull that often allow the cerebellum to herniate or to move into a position that causes it to get compressed and to malfunction. Now, the possible manifestations of these Chiari malformations are extensive, and that reflects how it affects the entire brain. So he describes patients who are acting in ways that might get them labeled as having something like a psychotic disorder or a personality disorder or obsessive compulsive disorder or an impulse control disorder, etc. And their symptoms dramatically and permanently improve once surgeons repair that Chiari malformation. Now, that by itself doesn't prove that it was this cerebellum causing all that dysfunction, but that's just one more piece of information in a large pile of information about the cerebellum. Now, remember that to execute movements, relatively small portions of the cerebellum are activated compared with the entire cerebellum. These regions compare sensory feedback with the feedback that it predicted it would get. Then it can find mismatches or errors, and then send signals to the motor cortex to correct the path or the amount of force that was used. Now, how does this relate to social learning? If a joke I tell does not result in laughter, does the cerebellum light up? If the parts of the cerebellum that are supposed to process errors in social communication are not correcting errors, does this result in, say, merely an absence of awareness of a social situation, or does it result in clumsy social interactions? What happens for more complex feedback, like facial expression? If the cerebellum is malfunctioning, does this help explain why someone with autism might be able to recognize that someone is angry, but not be able to connect it to the context, and then react either with withdrawal or dysphoria or even aggression? The cerebellum seems to be a module for unsupervised learning where it has to figure out relationships without being given any explicit instructions. People who lack cerebellar function in certain areas may be able to compensate for this by kind of more supervised types of learning where they have others maybe specifically tell them how to act in certain situations, make it very concrete, what certain gestures or expressions mean, etc. Things like social stories and rehearsals might be helpful for this kind of learning. It's understandably more concrete and inflexible to learn this way, but it certainly is better than nothing. When someone says, "Hello, how are you?" you say, "Hello, I'm okay. How are you?" One of the researchers in this field is Dr. Anila DeMello. She's an assistant professor and John Hyten Scholar in autism research in the Department of Psychiatry and O'Donnell Brain Institute at UT Southwestern. Her research has linked language regions of our left frontal cortex to their corresponding regions of the cerebellar cortex, especially in processing semantic information. For example, the cerebellum lights up when presented with grammatically correct but implausible sentences. Her example was, "The donut sweeps the steps." I wonder what the cerebellum is doing when children read Alice in Wonderland for the first time, or when we see a magic show. In short, subjects with greater cerebellar activity during tasks involving identifying semantic errors were also better at those tasks. So it seems the cerebellum helps us with semantic tasks. In a similar study, when presented with very predictable sentences and asked to choose the next best word, like 2 plus 2 is 4 or boat, only a very small region of the cerebellum lights up. But when presented with something like, "The man looked at the seat or birds," the outcome is less predictable, so more of the cerebellum lights up. When presented with language that is completely non-predictable, such as "Bait asked best rent and asked if the next best word is act or sand," the cerebellum goes wild. She also studied cerebellar activation in social learning in a task that involved tossing a ball to different players who were supposed to toss the ball back. But in some cases, these players were unreliable. Now, the players being studied quickly learned who the other bad players were, and they stopped tossing the ball to them. Regions of the cerebellum not involved in motor functions appeared to be activated while having to make that decision, whether to throw the ball to someone or not. They then used TMS to inhibit the regions that were responsible for this change, the decision to throw the ball or not, and found that players no longer differentiated between those who threw the ball back and those who didn't. They were just as likely to throw the ball to a person who wouldn't throw it back than they were to anyone else. It appears that their ability to predict the future was impaired. DeMello also used TMS to model motor versus cognitive associated regions of the cerebellum, and they looked at this effect on speech. So for the motor regions, if the motor regions of the cerebellum were inhibited, then syllable articulation was affected. They had a hard time pronouncing words. But semantic fluency was preserved. They had the same number of words. This relationship was opposite when cognitive association regions were stimulated. So articulation was preserved, they could say words, but their fluency was impaired. They also demonstrated in separate experiments that the cortical regions associated with regions receiving excitatory TMS, so the cortical regions that are associated with these same cerebellar regions, experienced greater connectivity after stimulating only the cerebellar regions. Now, this is similar to what we might expect TMS to do if you stimulate like the dorsolateral prefrontal cortex for depression. It's not the dorsolateral prefrontal cortex alone that is thought to change our mood state, but it's the downstream effects on things like your anterior cingulate gyrus and the nucleus accumbens that appear to make the difference after you stimulate the dorsolateral prefrontal cortex. One more honorable mention that DeMello talks about is that through some method that I didn't quite understand, they were able to demonstrate that the activity in the cerebellum was not being driven by activity in the cerebral cortex, at least not to the same extent that activity in the cerebral cortex was being driven by the cerebellum. It was the cerebellum that was making things happen in the cortex more than it was the cortex making things happen in the cerebellum. Another fascinating fact, and I know I said one more already, but I can't help myself, is that while damage to the cortex early in life is often able to be overcome, there's a lot of brain's ability to repair itself and there's plasticity of functioning in the cortex. Damage to the cerebellum early in life results in generally persistent deficits, and the brain can't overcome these. Now let's consider autism. Take any group of humans with autism. Because the features of autism relate to complex social behaviors and personal interests, this group is necessarily a very heterogeneous mix of people. Neurodivergence is a relatively recent word that attempts to kind of capture this relationship. I mean, as the saying goes, if you know one person with autism, then you know one person with autism. It makes sense then that since the cerebellum is so widely distributed in its influence, it could play a central role in the features of neurodivergent humans. Think about what the cerebellum does. It fine-tunes our cognitive gymnastics, our social ballet, our semantic flexibility, our choice of behavior, and our adaptability to changing sensory stimuli. All of these are disorders of prediction. Now let me give a shout out to Sinha et al., who published a paper titled Autism as a Disorder of Prediction, and it's in the Proceedings of the National Academy of Sciences in October of 2014. In this paper, they discuss how many of the phenotypic features of autism, including insistence on sameness, sensory hypersensitivity, difficulties interacting with dynamic objects like moving cars, and difficulties with theory of mind, are all problems with making predictions about the immediate or near future. Additionally, what they call islands of proficiency include mathematics, static form coherence, visual search, block design tasks, calendar calculations, musical performance, and drawing abilities, which are on average better accomplished by those diagnosed with autism than with controls. And this may be because all these things represent rural-based phenomena. I mean, rural as in not rural as in the opposite of urban, but rural as in don't break the rules. In rule-based phenomenon, there is less uncertainty. If you know the rules, you can perform the task. This, combined with the tendency to restrict interests, gives autistic individuals areas of particular strength. The authors of this paper also make some predictions based on this hypothesis, including that individuals with autism will be found to have hyperplastic interests. What I think this means is that because of their impaired predictive abilities, other than strictly rule-based ones, they can learn those, they will experience more of the world as novel, which means they'll respond to things that neurotypical people think are mundane. People with autism might see them as particularly salient or interesting or something they need to avoid. The authors also hypothesize that individuals with impaired predictive abilities in general would have a reduced appreciation of humor. This is because one of the bases of humor is basically violating what is expected. Someone with autism might not be anticipating or expecting a comedian to act in a certain way and therefore would not be impressed when she violates that normative expectation. They might instead be uninterested or confused. Another predicted consequence of impaired ability for prediction is reduced motor anticipation. Now, the authors define this as reduced ability to adjust to things like uneven terrain with the same speed as someone without autism might adjust to uneven terrain. People with autism might also manifest this impaired motor prediction as poor postural control, which means that they would be more likely to be off balance or would experience a greater degree of sway of the midline when they're simply standing still. And there are some studies that support these predictions. I have only scratched the surface of what we know about the cerebellum, and humans have only scratched the surface of what can be known about the cerebellum, this most densely packed processor in our brain. And I could go on, but I need to stop. Wait, I'm not going to stop yet. One more thing, and I really mean it this time. So, cerebellar activation has consistently been shown to be less in individuals with autism than in controls, according to DeMello. However, we know that individuals with autism often have very specific and narrow interests, which is not actually atypical of other children, but it's the amount of time that neurodivergent children or people in general spend with their particular interest that is abnormal. DeMello and colleagues also looked at cerebellar activation in children with autism versus controls. They found that for stories that were not related to an autistic person's particular interests, that person did not have much activation in their cerebellum. However, when a story containing their interest was introduced, their fMRI started to look like control children who were also given highly interesting stories. So this is very cool because it suggests that highly rewarding stimuli may be able to make an autistic person's cerebellum function at least approximately more like a typical cerebellum. Thank you for listening. I am Dr. O, and this has been an episode of Psychiatric.